This lecture is on something we call dimensional analysis. And this extends well beyond fluid mechanics. This is perhaps the most general thing we do in this course. It extends beyond our main conservation laws, mass, momentum, and energy. It is useful far and beyond in mechanics even. And in some sense, it's also therefore the most important thing that we talk about. It's more likely you'll use this later in your career than anything else I teach. And I'm going to kind of illustrate it by an example that involves fluid mechanics, of course. And let's say we had a pipe of some sort. So I'll draw the usual walls of the pipe, and let's say it has some length L. Let's say it has a diameter D. Let's say it flows fluid at some velocity V, and it's some sort of mean velocity. So in 1D uniform flow, it would be the only velocity. We did that a lot in Reynolds transport theorem questions, but this could be also just some mean velocity with a realistic velocity profile, such as we get when we solve the differential flow equations. Let's say that the fluid has a density rho and viscosity mu. And let's say that we're interested in, the question is delta P sub L. It's the pressure drop per unit length. And so in this case it would be the pressure drop per length L, perhaps. But let's say we're interested in the pressure drop per unit length. And why? Well, let's say we want to buy a pump and we need to know how much pumping power it would take to push fluid at a certain rate through a certain pipe of a certain density and certain viscosity. And in general, we can't solve this. We can do our Reynolds transport theorem, but that needs the detailed flow everywhere. And we can solve the differential flow equations in those special cases where it's steady and basically laminar flow. I'll define that later. In general, you can't do that either. And so you can do a series of experiments to try to figure this out. So let's plan a series of experiments. We don't want it just for one fluid. We want to kind of know in general what this would be for different fluids of different densities and viscosities and different velocities. And so we might plan an experiment where we vary. Well, we'll be calculating this delta P sub L, and we might vary the flow velocity. So you'd set it up, move the fluid through at different speeds, and measure the pressure drop per unit length. And perhaps that, I guess we'd expect it to go up. And in this case, we would say that rho, mu, and diameter are all constant. But that doesn't tell us anything about how this would depend on viscosity. And so maybe we would plan a second set of experiments. Where we would vary viscosity, and we'd measure this delta P sub L, and I guess we'd expect that to kind of go upward also, more viscous, harder to push fluid through the pipe. And now we would keep rho velocity and D constant. And so you can change. Liquids have a property often that you can change the temperature, you change viscosity without changing density. And so maybe you could heat a fluid of a particular type to do this study. Diameter. Clearly, you would expect to have less pressure drop for larger diameters, but we could do a little experiment here. Calculate our delta P sub L. We'd expect it to go down, probably less force required to push through larger diameters, and we'd keep rho, viscosity, and velocity constant as we changed diameter. And of course, the last set of experiments to kind of round this out, we would change density. And delta P sub L, we'd measure that, and it's really unclear. I expect it would go down here, and we would keep viscosity, velocity, and diameter constant. In this case, for that set of experiments. So it's 4 sets of experiments, and it's problematic in many ways. For one, I wouldn't even know how to do this where you would be changing density and keeping viscosity constant. It's a lot of work. This one, while you change this flow rate, is relatively easy. Changing viscosity is hard. You have to do different pipes for different diameters, and maybe different compression of different gases, and you get different densities, but then keeping the viscosity constant, it would be hard. But let's say you did this, because it's important. We flow so much stuff through pipes. If we can do that efficiently with the right size pumps, it really is a big engineering deal. It's still extremely limited. And so this is both hard / impossible. It's also limited. It's really just 4 curves through what's really a 4-dimensional space. What we're really doing here is sampling part of a function. What's underlying this whole approach is that we're interested in this delta P sub L, and we expect it to be a function of these other things. The fluid properties, density and viscosity, the velocity and diameter. And we planned out experiments in which we would vary each one of those, and those were hard. But this is a 4-dimensional space of these parameters. You could draw axes. That would be the d-axis, the v-axis, the mu-axis, and the rho-axis. And if you can barely draw 3-dimensional axes on a piece of paper, I would not know how to do 4-dimensional. But we would only have then just lines within this 4-dimensional space, these four curves, and it wouldn't represent all the parameters. And so it seems hopelessly complicated to really map this important engineering quantity out until you recognize this, that the physics can't depend upon the dimensions. And by dimensions here, I mean things like kilograms, meters, seconds, or whatever unit system you're in. The physics can't depend on those. Those are labels we make up. And so, let me just say that, but the physics cannot depend upon the dimensions, kilograms, meters, seconds, or pounds, feet, seconds, however they're defined. We made up These were useful ideas, putting these dimensional quantities, for our uses of them. We as people made these up for certain reasons. But the physics doesn't care if it's 10 kilograms per meter cubed or 1,000 kilograms per meter cubed if it's water. It doesn't care that it's 10 meters per second or 10 feet per second. It needs to have the same behavior regardless of which dimensions we use. And that tells us that the physics wrapped within this expression needs to access terms that don't have any dimensions. That tells us that in order to get rid of dimensions, we need to combine these terms in such a way that they divide out, essentially. And when you don't have dimensions on them, then you're getting to the core of physics. Then it doesn't say kilograms anymore. It doesn't say feet anymore. It just says some statement of physics that doesn't depend on those. And so let me be more specific about this. So this thing we're looking for, this delta P sub L, well, that has dimensions, and I'll use this notation for it, the equal sign with a little dot on it. Well, a pressure is a force per length squared, and it's per unit length. And so it's force per length cubed, or I'm going to say that the dimensional force is a mass times length per time squared, and then we've got this length cubed here, and so this has dimensions of a mass time squared length squared. So our answer in a useful set of units would be a mass per time squared length squared, kilograms, second squared, meters squared, for example. But the physics can't depend upon that. And so what I'm going to do is write down the dimensions of all of the variables involved, or the other four here. There's velocities, which is a length per time. There is a density, which is a mass per length cubed, kilograms per meter cubed. There is a diameter, that one's nice and easy, which is a length. And then there's viscosity, which is the one you look up because it's so hard to remember. It's a mass per length time. So you go to the front of the book and you see that one way to write this is kilograms per second, meters second, for example. So those are all the dimensions. And so I've been trying to emphasize here that the root physics of this can't depend on any of these, because these are things we ascribe to the problem in our description of it. And so what that means is that the parameters involved here, the variables, have to appear in such a way that these dimensions divide out. And so let me take delta P sub L here. And that has dimensions of mass T squared L squared, as I had up there. And let's figure out ways to combine these other parameters to get rid of these. And I say, well, you know what? I know it can't depend on mass, it can't depend on kilograms, so let me divide this through by rho. And so on this side, that would be a mass per length cubed. And I can come over here, and you see why I divided by rho is that there are no longer any masses on this side. Now, I'm not done yet because it still has a time squared here. And so, well, I want to get rid of the time squared. And so, you know what? I can also divide by velocity squared. And I'm just doing this by inspection. I'll give you a systematic way later. So, velocity squared. And so if I do velocity squared over here, that's a length squared per t squared. And you can see why I did that, because now that t squared and that t squared cancel. And what do I have here? This is 1 over L squared, and this is 1 over L. It's an L squared over L cubed. And so I need to multiply by an L. And I see I have an L here in the D. I'm going to go in there with that. That gives me an L on this side, and then I have L over L squared and L squared over L cubed, and those are all canceling. And so together this is a non-dimensional group of variables. So it's not unique. There are other ways to combine things and form non-dimensional groups, but it's a candidate to participate in the root physics because it doesn't have these dimensions that we ascribe to the numbers on it. And look, we've used all of the variables except for viscosity. And so let me show you another non-dimensional group here. And let's say, I'll just confirm this by inspection. Rho VD. So this one doesn't have viscosity. I want to use viscosity also. You can't leave any out. If you expect a dependence on viscosity, you better include that in your non-dimensional groups. And so what are the dimensions of this? Well, it's a mass per length cubed. It's a length per time. It's a length. Those are the three in the numerator. And then it's a mass per length time. And if you look at this carefully, the masses cancel. The 1 over t's cancel. And we have L squared over L cubed and 1 over L. The L's all cancel. So this also has dimensions of 1. It is non-dimensional. And we've used all the variables. And so what this tells us is that the core physics of this can be expressed this way. Delta P sub L over times D over rho V squared is some other function of rho VD over mu. We've used all the variables. We've formed two non-dimensional groups. And so now, though, the biggest thing you notice here is that this is a function with 4 dependencies. Getting these into non-dimensional groups, getting at the core physics of it, we came up with only one more variable. And so all the physics of this 4-dimensional space was an artificially large space. And in fact, it could span by just one parameter here. And this suggests an experiment that looks like this, where we say over here we're going to vary rho VD over mu, and over here we're going to measure delta PL D over rho V squared, and this should have some universal behavior. And so one set of experiments is sufficient to do in place of all of those others. And so you can see there's no fluid mechanics that came into this at all. This really was anything that had this property where there was something you wanted that depends on other things. Knowing it's a physical system of some form, it has this property. It can't depend on these dimensions. The only way to get rid of them is that they cancel. By inspection, we found one set of ways of combining these such that they cancel. We came up with a new equation where this delta P D over rho V squared depends only on this combination of terms. And that collapsed this 4-dimensional space of dependencies into 1-dimensional space. You can do one set of experiments as easy as possible. I think I would take the one where the diameter is fixed and you're using water and with a constant density and viscosity, and you vary the velocity. And you make this plot, and then you could go and later on and say, well, you know what, I've got glycerin, some viscosity, some density, flowing at such and such speed through some diameter pipe. So therefore, I'm here on this, and then I can read this off, and you can figure out what the pressure drop is.